Good morning, everyone. This is an audio recording for the visually impaired student from the book Pradeep Physical Chemistry, Volume 3 by Dr. S. C. Khetrapal. Physical Properties and Molecular Structure. Introduction. The various methods based upon the used for the study of molecular structure may be broadly classified into the following two types. Method 1. Method based upon the study of physical properties of the substance such as first is molar refraction, second paracore based upon surface tension, third optical activity, fourth dipole moment, fifth magnetic susceptibility. 2. Spectroscopic method such as first is rotational and vibrational spectroscopy, microwave and infrared spectroscopy. Second, electronic spectroscopy, UV and visible spectroscopy. Third is Raman spectroscopy. Fourth is NMR or nuclear magnetic resonance spectroscopy. The study of molecular structure on the basis of physical properties is based upon the fact that the physical properties listed above are additive as well as constitutive. An additive property of a molecule is defined as that property, the total value of which is the sum of the values of its constituent atom. A constitutive property of a molecule is defined as that property which depends upon the constitution of the molecule is that arrangement of atom within the molecule and the presence of multiple bond ring etc. in the molecule. Spectroscopic method have already been discussed in chapter 3. Now in this chapter we shall take up a brief discussion of three important physical properties, namely optical activity, dipole moment and magnetic susceptibility one by one. Optical activity. Definition. Plane polarized light. If a ray of light travel in any direction, it has vibration in all direction at right angle to the path of propagation, figure 5.1. If this light is passed through the nickel prism, then the light which emerges out of the prism is found to have vibration only in one plane. This light is called plane polarized light. The nickel prism thus used is called a polarizer. A nickel prism devised by the scientist Nicol consists of two prisms joined together as shown in figure 5.1. Each of these prisms is made out of a substance called Iceland spar or calcite, which is mainly CaCO3. If a single prism is used, it is found that two beams of light comes out, each of which is plane polarized light, and the plane of the two are at right angle to each other. By combining with second prism, one of the beam undergoes total internal reflection and only one plane polarized beam comes out. Instead of nickel prism, a Polaroid is also sometimes used. It consists of a film of cellulose acetate mounted between the two glass plates. Figure 5.1. Plane polarized light and its rotation. Optical activity. If the plane polarized light is passed through a plate of quartz or turpentine oil or the solution of sugar, then in a glass tube it is found that in the light that comes out, the plane of the polarized light get rotated. The substance like quartz, sugar, etc., which rotate the plane of polarized light are called optically active substance, and the property of a substance to rotate the plane of the polarized light is called optical activity. The substance which rotate the plane of the polarized light to the right are called dextro-rotatory, Latin dexter means right, and that whose rotate the plane of the polarized light to the left are called levio-rotatory, Latin levius means left. The method of observing the rotation of the plane of polarized light is based upon the following principle. If the plane polarized light is passed through another nickel prism which has its axis parallel to that of the first nickel prism, the light passes through the brightness and is observed through the eyepiece, figure 5.2a. On the other hand, if the second nickel prism is placed with its axis at right angle to that of the first prism, called crossed position, the light is completely cut off and field of view in the eyepiece is dark, is at figure 5.2b. At all other position the brightness is less, but there may not be complete darkness. It is observed that if the two nickel prisms are at the crossed position, so that the field of view is completely dark, and then the optically active substance is placed between the two prisms, the field of view becomes somewhat bright. The second prism has to be rotated through a certain angle about the line of propagation of light to get complete darkness again. This clearly shows that after passing through the optically active substance, the plane of the polarized light has been rotated. That the degree of rotation depends upon the rotation required to be given to the second nickel prism to get the darkness again. Thus, just as the first prism polarizes the light and is called polarizer, the second prism analyzes the light and is called analyzer. Figure 5.2a and figure 5.2b. Specific rotation. The angle in degree through which the plane of the polarized light is rotated on passing through the solution of an optically active substance depend upon the following factor. First one is the nature of the optically active substance. Second, concentration of the solution in gram per ml. Third is length of the solution is at the length of the tube through which the light passes in decimeter. Fourth is wavelength of the light used. Fifth is temperature of the solution. Thus, if m gram of the substance are dissolved in V ml of the solution, so that the concentration of the solution is m by V gram per ml. L is the length of the tube in decimeter and alpha is the angle of rotation in degree. Then it is found that alpha is directly proportional to concentration in gram per ml into length of the cube in decimeter. Alpha is directly proportional to m by V into L, or alpha is equal to alpha T lambda m into L divided by V. That is equation 1, where alpha T lambda is a constant characteristic of the nature of the substance and depend upon the wavelength lambda of light used and the temperature of the solution T degree Celsius. If daylight of the sodium vapor lamp light is used and the temperature of the solution is 25 degree Celsius, then it is written as alpha 25 degree T. This constant is called specific rotation of the substance. Thus, from the above equation, alpha T lambda is equal to V into alpha upon L into M. Now, if M is equal to 1 gram, V is equal to 1 ml and L is equal to 1 decimeter, then alpha T lambda is equal to alpha. Hence, specific rotation of a substance may be defined as the angle of rotation produced when 1 gram of the substance is dissolved in 1 ml of the solution, is that concentration of the solution is 1 gram per ml and the length of the solution through which the light passes is 1 decimeter. In all reported values of alpha T lambda, the concentration of the solution is taken in gram per 100 ml of the solution. Thus, if the C gram are dissolved in 100 ml of the solution, then we may put M is equal to C and V is equal to 100. This gives from equation 2. Alpha T lambda is equal to 100 into alpha upon L into C for solution. That is equation 3. Further, if instead of solution substance taken in a pure liquid or a solid, then M by V is replaced by density D of the pure substance. This gives from equation 2. Alpha T lambda is equal to alpha upon L into D for pure liquids or solid. That is equation 4. In case of pure solid, L is taken as the thickness of the solid in decimeter. Fourth is molar rotation. The molar rotation is obtained by multiplying the specific rotation with the molecular weight m of the substance and dividing the result by 100 to reduce the magnitude of the number. It is usually represented as mt lambda. Thus, mt lambda is equal to m into alpha T lambda upon 100. That is equation 5. Measurement of optical activity is at the angle of rotation alpha. The instrument used for the measurement of the amount of rotation in degree caused by an optically active substance to the plane of the polarized light is called a polarimeter. The principle of this instrument has already been discussed. It consists essentially of two nickel prism, one called the polarizer and the other called the analyzer. Both of these are fitted on the opposite end of the same metal tube. However, the polarizer is fixed, but the analyzer cannot be rotated about the axis of the tube. In between the polarizer and the analyzer, there is a space for keeping the glass tube containing the solution. The glass tube is usually 5 cm, 10 cm, 20 cm and 25 cm and has glass window on both ends. A circular scale is fitted on the metal tube near the analyzer as shown in figure 5.3. Figure 5.3 shown principle of a polarimeter. In the processor, first of all monochromatic light from a suitable source, usually sodium vapor lamp, is passed through the instrument without placing the tube containing the liquid or the solution. The light emerges out of the analyzer is viewed through the eyepiece. The analyzer is then rotated slowly till the field of view is completely dark. This gives the initial reading of the instrument. Now the tube containing the liquid or the solution of known concentration is placed and the shutter closed, not shown in figure 5.3. On seeing through the eyepiece, the field of view is no longer found to be dark. The analyzer is rotated slowly till the field of view is completely dark again. This gives a final reading. The difference between the final reading and the initial reading gives an angle of rotation alpha. It comes out to be positive, the substance is dextro-rotatory, and if it is negative, then it is called levio-rotatory. Modern instruments have numerous improvements over the simple type. However, the basic principle remains the same. Optical activity and chemical constitution. Optical activity is a purely constitutive property. It depends upon the arrangement of atoms within the molecule. It has been observed that the organic compounds which are found to be optically active contain at least one carbon atom to which 4 different atoms or group are attached. Such a carbon atom is called an asymmetric carbon atom and is usually shown by putting a sign of star over it. A very simple example of such a compound is that of lactic acid as represented below. Quite often, the instrument is used for finding the concentration of the sugar solution from an instrument measured value of alpha and known value of alpha and the formula given in equation 3 in session 5.2.1. The instrument thus used is called secarimeter. It is found that such a substance exists in two forms, one of which rotates the plane of polarized light to the right and is called dextrorotatory D form or plus form. Another which rotates the plane of the polarized light to the left and is called levorotatory L form and minus form. The two forms has the same constitution. In each form, the asymmetric carbon atom is attached to the same four atoms or group, but differ in their configuration, arrangement of atoms or group in space. Thus, the two forms are space isomers called optical isomers. Liebel and Van 't Hoff pointed out the difference in the two forms by suggesting that in case of such molecule, the asymmetric carbon atom is present in the center of a regular tetrahedron and the four atom or group attached to it are present at the corner of the tetrahedron. This gave rise to the two different spatial arrangements which were like the mirror image of each other as shown in figure 5.4 below. Spatial difference in D and L form of lactic acid shown in figure 5.4. The above two configurations are different in the sense that they are not superimposable over each other, thus the two forms are related to each other as the right hand is to the left hand of the same person. The above two forms may be represented in a simplified ways as follow. In the form 1, the arrangement from H to OH is clockwise, and in the form 2, the arrangement from H to OH is anticlockwise. Hence, if one of them is dextrorotatory, the other is levorotatory. However, by mere inspection of the configuration, it is not possible to predict as to which form is dextro or levo. The two forms are said to be enantiomorphous. Greek enantiom means opposite and morph means form. Further, if equimolar quantities of the two forms are mixed together, a third form is obtained, which is optically active. It is obviously due to the fact that the rotation caused by one form to the right is nullified or compensated by the equal rotation caused by the second form to the left. This process is called external compensation, and the substance thus obtained are called racemic mixture or DL form or plus minus form. This form can be separated into D and L form by suitable method. In case of compound containing two asymmetric carbon atoms is that tartric acid, a fourth form is also found to exist. In this form, the rotation caused by half of the molecule is compensated by the other half within the molecule as shown in figure 5.5 for tartric acid. This form, which is optically inactive due to internal compensation, is called mesoform. Lastly, it may be mentioned that optical activity is found not only in the organic compound containing an asymmetric carbon atom but also in the compound which contain other asymmetric atoms like nitrogen, sulfur, silicon, cobalt, etc. Further, some compound may not contain as an asymmetric atom but are optically active because a molecule as a whole is asymmetric. If that is at no plane can divide the molecule into two identical halves. Thus, it may be concluded that the optical activity is a property related with asymmetry of the molecule. Hence, optical activity can be used to test the presence of asymmetry in the molecule. Numerical problem on optical activity. When compound like nitric acid are synthesized in the laboratory, there is equal possibility of formation of D and L form. Thus, the equal amount of D and L form get mixed up and a racemic mixture is usually obtained. The optical activity of quartz is due to the peculiar arrangement of molecule within the crystal or spiral arrangement. Dipole moment. General introduction. Polar and non-polar covalent bond. A covalent bond is formed by the mutual sharing of electron between the two atoms. If the two atoms are identical, is that in the H2, Cl2, etc., the shared pair of electrons is attracted equally by both the atoms and hence it remains exactly in the center of the two atoms as shown below. Thus, neither of the two atoms in such molecule acquires positive or negative charge. The bond thus formed between the two identical atoms is called non-polar covalent bond. On the other hand, if the two atoms are dissimilar, is that in the HCl molecule, chlorine atom is more electronegative than the hydrogen atom. Hence, the electron pair is more attracted towards the chlorine atom than towards the hydrogen atom. In other words, the shared pair of electron is more displaced towards the chlorine atom than towards hydrogen atom. As a result, the chlorine atom of the molecule acquires a slight negative charge while the hydrogen atom of the molecule acquires a slight positive charge. The bond thus formed between the two dissimilar atoms having slightly different electronegativity is called a polar covalent bond, and the molecule is called a dipole because it has developed positive and negative pole. Thus, the situation in HCl may be represented as shown in figure 5.6. Dipole moment of a diatomic molecule. The extent of polarity or polarization of a molecule is expressed in terms of dipole moment, which is defined as follows. The dipole moment of a polar diatomic molecule is that the product of the charge on each end of the molecule and the average distance between the center of their nuclei is that the bond length. In general, for a polar diatomic molecule AB in which atom B is more electronegative than A, if plus Q is the charge on the end A and minus Q on the end B of the molecule, and D is the average distance between the center of the two nuclei, then the dipole moment of the molecule AB is given by mu is equal to Q into D. Obviously, the molecule is non-polar. Q is equal to 0 and hence mu is equal to 0. Unit of dipole moment. The charge present on end of the molecule is usually of the order of 10 raised to power minus 10 ESU, and the distance between the atom is that bond length is usually of the order of 10 raised to power minus 8 centimeters at angstrom unit. Therefore, mu must be of the order of 10 raised to power minus 10 into 10 raised to power minus 8, that is equal to 10 raised to power minus 18 ESU centimeter. This value is called 1 by after the name of the pioneer workers in this field. Thus, 1 divided is equal to 10 raised to power minus 18 ESU centimeter. Vector nature of the dipole moment. The dipole moment is a vector quantity. It has both magnitude as well as direction. It is therefore represented by an arrow pointed from the positive, and the negative end of the dipole of the molecule is at plus to minus. Fifth, dipole moment of a polyatomic molecule. In a polyatomic molecule containing more than two atoms, every two bonded atom have their dipole moment. Thus, this is called the bond moment. The net dipole moment of the polyatomic molecule is the resultant of the different bond moment. Obviously, the resultant will depend upon the direction of the bond. Thus, if a molecule AB2 contain two AB bond at an angle of theta, and mu AB is the angle value of each bond moment, then the dipole moment of the molecule will be mu is equal to 2 mu AB cos theta by 2. As mu is known from experiment, therefore, knowing the value of theta, the method is usually used for the calculation of bond moment. Alternatively, knowing the value of mu and mu AB, the method can be used for the calculation of theta and hence for predicting the shape of the molecule, as later discussed in session 5.3.3. The experimentally observed value of dipole moment of the same common molecule and the calculated value of bond moment of the same common bond are given in table 5.1 and 5.2 respectively. Table 5.1, dipole moment in debye units of some common molecule. For a more general molecule ABC with two bonds AB and AC having bond moment mu1 and mu2 are inclined at an angle theta, the dipole moment of the molecule by parallelogram law will be mu is equal to under the root mu1 square plus mu2 square plus 2 mu1 mu2 cos theta, or it may be calculated graphically. Table 5.2, bond moment in debye unit of some common bonds. The resultant dipole moment of the groups like NO2, NH2, CH3, etc. have also been reported. These are called group moment. Their values depend upon whether the group is attached to an alkyl radical and an aryl radical. The values of few groups are given below. A negative value of the group moment means that the group is more electronegative, and a positive value means that the group is less electronegative than the alkyl or the aryl radical या benzene ring. Electrical polarization of molecule. Every molecule is made up of positively charged nuclei and negatively charged electron cloud, as shown in figure 5.9a. The center of positive charge coincides with the center of negative charge. Hence, when such a molecule is introduced between the two plates of an electrical field, the positive charged nuclei, and hence the center of the positive charge is attracted towards the negative plate, whereas the negatively charged electron cloud is attracted towards the positively plate of the electric field. As a result, the molecule gets distorted, as shown in figure 5.9b. This is called polarization, and the molecule and the distorted molecule with positive and negative end is called an electric dipole or dielectric. The molecule remains polarized so as the electric field is applied, but goes back to the original state as soon as the electric field is switched off. That is why this type of polarization is called induced polarization, and the electric dipole formed is called induced dipole. Since even after polarization the molecule is neutral as a whole, this means that the positive charge on one end must be equal to the negative end on the other end. Suppose this charge is q, and if d is the distance of separation between the charges, then the dipole moment of the induced dipole, called the induced dipole moment, represented by mu I, will be given by mu I is equal to q into d, and equation 1. Evidently, the value of mu I will depend upon the value of the molecule and the strength of the electric field. Say x, we write mu I is equal to alpha into x, equation 2, where alpha is a constant and is called the polarizability of the given molecule. Alpha is further found to be related to the dielectric constant D of the molecule present between the plate. Is that the molecule being studied according to the equation put forward by Clausius and Mosety d minus 1 upon d plus 2 m by rho, that is equal to 4 by 3 pi n alpha. That is equation 3. Where m is the molecular mass of the molecule and rho is the density of the molecule and is the Avogadro's number. Clausius-Mosety equation. Suppose an electrostatic field is applied to the two plates of so that they are charges. Suppose the strength of the uniform electric field produced between them is E naught. Now if a non-polar medium is placed between the plate, the strength of the dielectric field will be reduced to E because the induced dipole called dielectric act in opposition to the applied field and hence partially neutralize the charge of the plate as shown in figure 5.10. The ratio E naught by is called the dielectric constant D or relative permittivity of the medium. Now electrostatic, it can be shown that E naught is equal to E plus 4 pi I, where I is the induced dipole moment per unit volume is that I is equal to mu I into n, where mu I is the induced dipole moment in a single molecule and n is the number of molecule per cc. Dividing both sides of equation 4 and E and putting E naught by E is equal to D, we get D is equal to 1 plus 4 pi I divided by E or D minus 1 E in D minus 1 into E, that is equal to 4 pi I, that is equation 5th. The intensity of the electric field strength X acting on each molecule is calculated by supporting that a unit charge is enclosed in a small spherical cavity which is large as compared with the size of the molecule but small in comparison with the distance between the plate. The electric intensity X is that then made up of the following part. The system consisting of two charge plate act as condenser. The capacity of the condenser is in the inverse ratio of E naught by E. Hence dielectric constant is defined as the ratio of the capacity of the condenser with the given substance to that with vacuum between the plates. First, the field strength of the charge on the plate is equal to E naught, and second is the charge induced on the surface of the dielectric in contact with the plate, that is equal to minus 4 pi I. Third is that charge induced on the surface of the spherical cavity, that is equal to plus 4 by 3 pi I. X is equal to E naught plus 4 by 3 pi I minus 4 pi I. Substituting the value of E naught from equation 4, we get X is equal to E plus 4 pi I plus 4 by 3 pi I minus 4 pi I, that is equal to E plus 4 by 3 pi I. That is equation 7. Substituting the value of 4 pi I from equation 5, we get X is equal to E plus D minus 1 upon 3 into E, that is equal to 1 plus D minus 1 upon 3 into E is equal to D plus 2 upon 3 into E, that is equation 8. From equation 7 and 8, E plus 4 by 3 pi I is equal to D plus 2 by 3 into E, or D plus 2 upon 3 minus 1 into E, that is equal to 4 by 3 pi I, or D minus 1 upon 3 E is equal to 4 by 3 pi I. I is equal to mu I into n as already defined, and alpha x into n. Mu I is equal to alpha x already defined, that is equal to alpha D plus 2 upon 3 E into n, and that x is equal to D plus 2 upon 3 into E from equation 8. Equation 9 becomes D minus 1 upon 3 into E, that is equal to 4 by 3 pi alpha into D plus 2 upon 3 into E into n, or D minus 1 upon D plus 2, that is equal to 4 by 3 pi n alpha, that is our equation 10. If rho is the density of the substance placed between the charge plate is that of the medium between the charged plate, and m is the molecular mass, then molecular value of the volume of the substance, that is equal to m by rho. If n represent Avogadro's number and number of molecule per unit volume, that is n is equal to n upon m by rho, that is equal to n rho by m, that is our equation 11. Substituting this value in equation 10, we get D minus 1 upon D plus 2, that is equal to 4 by 3 pi n rho by m into alpha, or D minus 1 upon D plus 2 m by rho, that is equal to 4 by 3 pi n alpha, that is our equation 12. As all quantity on the right hand side of equation 12 are constant, alpha being constant for a given substance independent of temperature, therefore the quantity on the left hand side of equation 12 must also be constant independent of temperature and depending upon the nature of the molecule. This quantity is called molar polarization and is represented by P. Further, as a applied field produce and induce charges in the molecule by the relative displacement or distortion of electrons and nuclei, P is often called induced or distortion polarization and is represented by Pi or Pd. Therefore, Pi or Pd, that is equal to D minus 1 upon D plus 2 m by rho. Equation 13. Induced molar polarization is defined as the amount of polarization induced in 1 mole of the substance when placed between the plate of an electric field of unit strength. From equation 13, it is evident that the unit of Pi will be same as those of m by rho or molar volume. Hence, Pi is usually expressed in centimeter cube per mole. Expression 13 giving the relationship between dielectric constant and polarizability was first derived by Maury in 1850 and Clausius in 1879 and is called Clausius equation. Effect of temperature on polarization. Using equation 13, the value of molar polarization have been determined for a number of substances. It is found that whereas molar polarization of number of substances such as oxygen, CO2, N2 and CH4 are constant and independent of temperature, the polarization value of some other substances such as HCl, CHCl3, C6H5NO2 and CH3Cl do not comes out to be constant but decrease with increase of temperature. The observation has been on the basis of measurement of dipole moment and the study of molecular structure as explained below. In case of molecules such as HCl, CHCl3, etc., their center of positive and negative charge do not coincide with each other, thus they possess some dipole moment even in the absence of electric field. The dipole moment thus possessed by the molecule is called permanent dipole moment. In the absence of electric field, these permanent dipole are oriented in a random manner due to their thermal agitation as they are shown in figure 5.11. However, in the presence of an electric field, the two disturbing effect takes place. They are, first one is the electric field will tends to rotate the orient these dipole in the direction of the field. Second, the electric field will tends to polarize the molecule. If the molecule was stationary, the dipole would have been oriented perfectly parallel to the electric field is that at right angle to the plane of the electric field. However, due to thermal agitation, they take up position in between that of the original state and the perfectly parallel state as shown in figure B in figure 5.12 for any one permanent dipole. Thus, in case of molecule possessing permanent dipole, the right hand side of equation 13 will give the total polarization Pt, which will be the sum of induced molar polarization and the orientation molar polarization PO, as that Pt is equal to d minus 1 upon d plus 2 into m by rho, that is equal to Pi plus P naught, that is our equation 14. As mentioned earlier, the induced polarization is given by Clausius-Maury equation with Pi is equal to 4 by 3 pi and alpha, that our equation 15. The orientation molecular polarization is given by the equation put forward by d with P naught is equal to 4 by 3 pi n into mu square upon 3 kt, that is equation 16. Where mu is the permanent dipole moment of the molecule, k is the Boltzmann constant, that is equal to r by n, and T is the temperature. Substituting the value of Pi or P naught from equation 15 and 16 in equation 14, we get Pt is equal to d minus 1 upon d plus 2 into m by rho, that is equal to 4 by 3 pi n alpha plus alpha 4 by 3 pi n into mu square upon 3 kt, that is equation 17. Measurement of dipole moment. First one is the vapor temperature method. The above equation can be written in the form of Pt is equal to A plus B by T, where A is equal to 4 by 3 pi n alpha and B is equal to 4 pi n mu square upon 9k are constant for the given substance. This equation is preliminary applicable to gases and vapor. Thus, if Pt is plotted against 1 by T, a straight line graph will be obtained if the molecule possessed permanent dipole. The slope of the plot will be given by B is equal to 4 pi n mu square upon 9k. That is equation 19. From this equation, the permanent dipole moment mu of the molecule can be calculated as all other quantities are constant whose values are known. Solving equation 19 by putting the value of the various constant, we get mu is equal to 0.0218 under the root b into 10 raised to power minus 18. The straight line plot of for a few substances with and without permanent dipole is that polar and non-polar molecule are shown in figure 5.13. It may be seen that where Pt varies with temperature for HCl, CH3, Cl, etc. possessing permanent dipole, there is no effect of temperature on substance like CH4, CCl4, etc. which do not have permanent dipole and they possess only induced molar polarization. Method of measurement of dipole moment. As explained above, the basic equation for the determination of dipole moment is Pt is equal to d minus 1 upon t plus 2 into m by rho, that is equal to A plus B by T, that is equation 20. A and B are constant with B is equal to 4 pi n mu square upon 9k. Thus, the experiment involved the determination of the dielectric constant D and the density rho at a different temperature T. The value of Pt are then calculated and plotted against 1 by D for if Pt is found to vary linearly with 1 by T, the substance possesses a permanent dipole moment and the value of the dipole moment mu is calculated from the slope of the line. On the other hand, if Pt is found to be independent of temperature, the substance does not possess any permanent dipole moment, it is non-polar. The dielectric constant required in the above equation is determined by first measuring the capacity of a condenser in vacuum between the plate C naught and then measuring the capacity of the same condenser when filled with the given substance C. The dielectric constant of the given substance is Z given by D is equal to C by C naught, that is equation 21. Second, refraction method. According to Clausius-Moser equation, the induced or distortion molar polarization Pi or Pd of the molecule is given by Pi or Pd, that is equal to D minus 1 upon D plus 2 into m pi rho, that is equal to 4 by 3 pi n alpha, that is our equation 22. As D is the dielectric constant, is a pure number, molar polarization P is simply molar volume of the material. Further, it is already been explained that it is independent of temperature. The substance is non-polar and does not have a permanent dipole moment. For such molecule, it was derived as by J.C. Maxwell in 1881. Then the dielectric constant of the substance is related to its refractive index for light of long wavelength according to the equation D is equal to n infinity square. Substituting this value in equation 22, we get PD is equal to n infinity square minus 1 upon n infinity square plus 2 into m pi rho, that is equal to 4 by 3 pi n alpha, that is our equation 24. Where n infinity square cannot be found by extrapolation to infinite wavelength, the value of refractive index is measured with visible light. This is because visible light can displace only electron, whereas a positively charged nuclei remains unaffected. Thus, the distortion polarization can be considered to be the sum of electron polarization Pe and atom polarization Pa. Is that Pd is equal to Pe plus Pa. Thus, polarizability alpha is also accordingly made up of the two parts alpha E and alpha A, called electron polarizability and the atomic or nuclear polarizability respectively. The find total value of Pd. It is therefore necessary to measure the refractive index using refractive infrared rays because they can displace the heavy atomic nuclei as well as electron, but measurement of refractive index with infrared radiation is difficult. Hence, the problem is solved by finding electron polarization by measuring the refractive index and using visible light D line. Zp is equal to n square minus 1 upon n square plus 2 into m by rho, that is equation 25. As an approximation, 5% of this value is added to it to account for Pa to get the total value of Pd. Is that Pd is equal to Pe plus Pa with 5% of Pe. Then as before, total polarization Pt of a molecule possessing a permanent dipole moment is the sum of the two terms, the first called distortion polarization Pd and the second called the orientation polarization Po. Due to permanent moment possessed by the molecule, hence we can write Pt is equal to Pd plus Po. Putting the value of Po from by equation with P naught is equal to 4 by 3 pi n into mu square upon 3 kt, that is equation 27. Equation 5 becomes Pt is equal to Pd plus 4 by 3 pi n into mu square upon 3 kt, that is equation 28. Putting the value of the constant and simplifying, we get mu is equal to 0.0128 under the root Pt minus Pd into T, that is equation 29. Pt can be determined by finding the dielectric constant of the vapors at temperature T, and Pd can be found either by measuring the refractive index using infrared radiation or by approximation method explained above. This method is simpler than the temperature method because it involves the measurement only at one temperature. Dilute solution method. Equation 20 is applicable to gases and vapors only. For substances which are not gases or which cannot be converted into vapor, the following procedure is followed. First is the dilute solution. The given substance is prepared in a non-polar solvent such as benzene, Cl4, CS2, etc. The density of the dielectric constant of the solution are determined at various temperatures. At each temperature, the molar polarization of the substance of the solution PS is calculated using the relation PS is equal to D minus 1 upon D plus 2 into x1 m1 plus x2 m2 upon rho, that is equation 30, where x1 and x2 are the mole fraction of the substance and the solute in the solution m1 and m2 are their respective molecular masses, and rho is the density of the solution. Third, the molar polarization of the solution is related to the molar polarization of the solvent x1 and that of the solute x2, as PS is equal to x1 p1 plus x2 p2, that is equation 31. Thus, knowing the value of x1, x2 and p1, the value of p2, molar polarization of the substance being studied can be calculated. The value of P2 obtained at different temperature are plotted against 1 by T. The value of mu is then calculated from the slope of the line as explained earlier. Dipole moment and chemical concentration. Application of dipole moment. The knowledge of the dipole moment of a molecule can be applied in a number of ways to study its chemical constitution. A few important applications of dipole moment are briefly described below. In comparing the relative polarizability of molecule, polarities of molecule. For example, the dipole moment of HF, HCl, HBr, HI are 2.0, 1.03, 0.78 and 0.38 dBi respectively. This shows that the polar character of the molecule decreases as we move from HF to HI. Second, in calculating the percentage ionic character of a polar covalent bond. For example, the dipole moment of HCl is 1.03 dBi if the bond were 100% ionic each and would acquire full 1 unit charge is at 4.8 into 10 to the power minus 10 ESU. The bond distance is for in HCl is taken to be 1.275 angstrom is at 1.275 into 10 raised to power minus 8 centimeter. Hence, if HCl were 100% ionic, the dipole moment would have been 4.8 into 10 raised to power minus 10 into 1.275 into 10 raised to power 8 ESU centimeter. That is equal to 6.11 into 10 raised to power minus 18 ESU centimeter or 6.11 dBi. Actual value of dipole moment of HCl is equal to 1.03 dBi and percentage ionic character of HCl bond is 1.03 upon 6.11 into 100, that is equal to 17% approx. Third, in predicting the geometry or shape of the molecule, the fact that the dipole moment is a vector quantity and that a particular bond have almost a constant value of bond moment is very useful in predicting the shape of the molecule. A few cases are described below. First is diatomic molecule. A diatomic molecule is always linear irrespective of its dipole moment. B. Triatomic molecule. In triatomic molecule of the type AB2, there are two possibilities in this molecule. One bond. First is the dipole moment of the molecule may be 0 is that in case of CO2, CS2. This shows that in this molecule, one bond moment is equal and opposite to the other. Hence, the molecule must be linear is that as shown in figure. And the molecule may have a definite value of dipole moment is that mu for water is 1.84 dBi, mu for SO2 is 1.63 dBi. Obviously, in this case, the possibility of linear shape is ruled out. The two bonds must have a definite angle between them which can be calculated if we know the bond moment as discussed earlier in session 5.3.1. For example, the bond moment of HO is 1.6 dBi and the bond angle is calculated to be nearly 105 degrees Celsius. 105 degree. Thus 120. This H2 may be represented as shown in figure 5.14. Such molecules are called bent molecule and the shape is V shape. Tetraatomic molecule. In tetraatomic molecule of the type AB3, the two simple possibilities are the dipole moment of the molecule may be 0 is that in BF3. In such a case, all the 4 atoms must be in one plane and the angle between the bond must be equal is that in BF3 shown in figure 5.15. Such a shape is called planar trigonal. The molecule may have some definite value of dipole is that ammonia PF3 PCl3. It indicates that one atom lies out of plane of the rest of the atom. For example, the molecule of NH3 may be represented in figure 5.16. Such a shape is called pyramidal shape. Pentaatomic molecule. The pentaatomic molecule of the type AB for which we commonly comes out are CH4, CCl4, SiCl4 and SnCl4 etc. The dipole moment of all these molecules is found to be 0. This is possible only if these molecules have symmetrical or regular geometry so that the different bond moment cancel out each other. The experimental fact confirms that these molecules have tetrahedral shape as represented below. In differentiating the cis and trans isomers, the cis and trans isomers represented as the second possibility is that the atom may be in one plane but the angle between the bond may not be equal is that in ClF3. Then the shape is planar but not trigonal. It is clear that the trans form will be non-polar is that will have zero dipole moment, whereas this form will be polar, will have definite dipole moment. For example, in case of dichloroethylene, Potax is equal to Cl. This form have been found to have a dipole moment of 1.9 dBi, while the trans form is found to have zero dipole moment. Fifth, in differentiating the orthometa and para isomers, as benzene is a regular hexagon and its dipole moment is 0, therefore substituting two atom or group in the orthometa and para position, the di-substituted derivative will have different dipole moment for the orthometa and para isomers as shown below. Obviously, para will have zero dipole moment and meta will has less dipole moment than ortho. 6. In supporting the possibility of resonating structure. For example, the nitrous oxide molecule N2O has a small value of dipole moment 0.17 dpi. If the molecule is supposed to have any one of the following two structures, the dipole moment should be high, and this confirms that N2O molecule is a resonance hybrid of structure 1 and 2. Magnetic susceptibility. General introduction to some term used. Magnetic permeability. If the two magnetic pole of strength M1 and M2 are separated by a distance r, then the force F acting between them is given by F is equal to 1 by mu M1 into M2 upon r square. The quantity mu used in the above expression is called magnetic permeability of the medium between the pole. It is defined as the relative tendency of the magnetic line of force to pass through the medium as compared to that in the vacuum. For vacuum, mu is taken as equal to 1. Similarly, for air, mu is taken as approximately equal to 1. Diatomic, paramagnetic and ferromagnetic substances as mentioned above. For vacuum, mu is equal to 1. For other media, mu can be less than or greater than 1. If mu is less than 1, then the magnetic line of force prefer to pass through the vacuum rather than through the substance comprising the medium. In other words, the magnetic line of force are repelled away from the substances. Substances are said to be diamagnetic. On the other hand, if mu is greater than 1, then the magnetic line of force have greater tendency to pass through the substance rather than through the vacuum. In other words, the magnetic line of force are directed towards the substance. Such substances are called paramagnetic if mu is very high, of the order of 10 raised to power 3 or more. The tendency of the substance to attract the magnetic line of force is very high, and the substance is said to be ferromagnetic. Ferromagnetism is exhibited mainly by iron, cobalt, nickel and their alloy. It is a property of greater interest in the subject of physics only. In chemistry, we deal only with the diamagnetism and ferromagnetism. The behavior of diamagnetism and paramagnetism substances in a magnetic field is shown diagrammatically in figure 5.19. Third is magnetic susceptibility. As seen above, if any material is placed in a magnetic field, the strength of the magnetic field in the material is different from that in the vacuum. The strength of the magnetic field that thus present in the material is called magnetic induction. Figure 5.19. If H is the strength of the applied magnetic field and B is the magnetic induction in the given material, the two are related according to the equation B is equal to H plus 4 pi I, that is equation 1, where I represent the magnetic moment per unit volume in the material and is called intensity of magnetization. It may be positive or negative depending upon whether the material is paramagnetic or diamagnetic. The intensity of magnetization produced per unit strength of the applied magnetic field is called the specific magnetic susceptibility. It is usually represented by xi. Thus, mathematically, xi is equal to I by H, that is equation 2. It is this quantity which is usually measured experimentally in the study of magnetic properties of different material. Multiplying the specific magnetic susceptibility with the molar volume m by rho of the material, we get that as a magnetic what is called as magnetic susceptibility per mole, or molar magnetic susceptibility is usually represented by xi m. Mathematically, xi m is equal to m by rho into I by H, that is equation 3. The molar magnetic susceptibility may be defined as the intensity of magnetization induced per mole of the material by the unit field strength. Quite often it is convenient to deal with the quantity xi m in place of xi. Further, the magnetic induction B is related to the strength of the applied magnetic field H according to the equation B is equal to mu H, that is equation 4, where mu is the magnetic permeability of the medium is at the material placed between the pole. Also from equation 2, I is equal to xi H, that is equation 5. Substituting the value of B and I from equation 4 and 5 in equation 1, we get mu H is equal to H plus 4 pi xi H, or mu is equal to 1 plus 4 pi xi, that is equation 6. Since I in the above discussion is the magnetic moment per unit volume of the material, xi is in fact the volume susceptibility of the medium. However, for most of the practical purpose, we use mass susceptibility. It is obtained by dividing the volume susceptibility by the density rho of the material. Hence, we have mass susceptibility xi dash is equal to xi by rho, and xi is equal to rho xi dash. Substituting the value in equation 7, we get a mu is equal to 1 plus 4 pi rho xi dash, which gives xi dash is equal to mu minus 1 upon 4 pi rho, that is equation 8. This gives the relationship between the specific magnetic susceptibility and the magnetic permeability of a material of density rho in gram per cc. Since for diamagnetic substances mu is less than 1, therefore the specific magnetic susceptibility xi or psi dash is negative for such substance. On the other hand, for paramagnetic substances mu is greater than 1. Therefore, xi or xi dash is positive but small. For ferromagnetic substances, as mu is very large, so xi and xi dash is also very large. Measurement of magnetic susceptibility Gauss method. The magnetic susceptibility are generally determined by the method put forward by Gauss in 1889. It is shown in figure 5.20 and is briefly explained below. The material under examination is taken in a thin cylinder or a tube which is then suspended vertically with a wire from one arm of the balance between the two poles of an electromagnet such that the lower end of the cylinder is nearly in the middle of the poles of the electromagnet. The cylinder is now counterbalanced in this position by placing weight in the other pan of the balance. The current is now switched on into the electromagnetic. If the substance is paramagnetic, the cylinder will be pulled down so that more magnetic line of force can pass through it. On the other hand, the cylinder will be pulled down. On the other hand, if the substance is diamagnetic, the cylinder will be pushed upward so that the less magnetic line of force may pass through it. In the first case, some extra weight will have to be added into the pan, whereas in the second case, some weight will have to be removed from the pan to restore the balance. Since the change in the weight is equal to the magnetic force acting on the material, hence if delta m is the change in mass, then we have delta mg is equal to 1 by 2 xi minus ia into ah square, that is equation 9. Where g is the acceleration due to gravity, so that delta mg gives the change in weight. The right hand side is the magnetic force acting on the material of volume susceptibility xi, and where is the area of cross section of the specimen, h is the field strength, and xi is the volume susceptibility of the air. Value of xi is equal to 0.03 into 10 raised to power minus 6. Thus, using equation 9, the value of xi can be calculated. In the above calculation, the absolute value of the field strength h is also required. However, the necessity of measuring h and a can be eliminated if the experiment is first performed with substance of non-susceptibility using the same magnetic field and the same cylinder for taking this substance. Usually water is taken as a standard substance for this purpose. Thus evidently we will have delta ms upon delta mw, that is equal to xi s minus xi a upon xi w minus xi a, that is equation 10, where delta ms is a change in mass when the sample under examination is placed in the magnetic field, and delta mw is a change in mass when water is taken in the same cylinder and placed in the same magnetic field. Xi s is a magnetic susceptibility, volume susceptibility of the sample, and xi w and xi a are those of the water and air respectively. Magnetic susceptibility and molecular structure. A detailed study of the magnetic susceptibility of a large number of organic and inorganic compounds carried out by Pascal during 1908 to 1913 have revealed that, like many other physical properties such as molar refraction, paracore, etc., the molar magnetic susceptibility xi m is an additive as well as constitutive property. The value assigned to the various atoms and to the structural factor, double bond, triple bond ring, etc., can be obtained from the experiment determined value for a large number of element and compound. The value of magnetic susceptibility for some of the atoms and structural atoms are given in figure in table 5.3 below. Table 5.3 atomic and structural susceptibilities. The calculation of molar magnetic susceptibility of a compound for the atomic and structural values help us to decide between the alternate structure for a compound or to confirm the structure of the compound by comparing the calculated value with the experimental value. A few examples are illustrated below. Diamagnetic substances were studied for this purpose because their magnetic susceptibility is independent of temperature and is nearly same for substance in the gaseous and liquid state. Explanation of diamagnetism and paramagnetism. Electrons in an atom have orbital motion as well as spin motion. As they are charged particles, therefore their motion produces a small magnetic field. If all the electrons in a molecule are paired, the magnetic moment of the electron spinning in one direction is cancelled by the magnetic moment of the electron spinning in the opposite direction. The net result is that the substance has zero magnetic moment. If such a substance is placed in a magnetic field, small magnetic moment is induced in the substance in opposition to the external magnetic field. As a result, the substance is repelled by the magnetic field. This type of behavior is observed for the diamagnetic substances. Thus, diamagnetism is exhibited by those substances which contain paired electron only, is that no unpaired electron is present. On the other hand, if a substance contains some unpaired electron, the magnetic moment of the electron do not cancel out completely. Hence, the substance has a permanent magnetic moment of its own. In fact, each unpaired electron behaving like a micromagnet with a definite magnetic moment in such a substance is placed in an external magnetic field. The micromagnet will arrange themselves parallel to the external magnetic field, and the induced magnetic moment is insufficient to overcome the permanent magnetic moment of the substances. Substances are therefore attracted by the magnetic field instead of being repelled by it. This type of behavior is observed for the paramagnetic substances. Thus paramagnetism is exhibited by those substances which contain some unpaired electron. Determination of magnetic moment of a paramagnetic substance. As explained above, each atom, ion or molecule of a paramagnetic substance behave like a micromagnet with a definite inherent magnetic moment of magnitude mu m, which when such a substance is placed in the external magnetic field, the micromagnet tends to arrange themselves parallel to the applied field. However, this tendency is opposed by the thermal motion of the particle, because magnetic susceptibility of paramagnetic substances vary with temperature. Hence, actual arrangement taken up will depend upon the temperature. Langevin in 1905 put forward the following relationship between molar magnetic susceptibility Xi m and molecular magnetic moment mu m and temperature T. Xi m is equal to alpha m into mu m square n upon 3 kt, 11 equation, where n is the Avogadro's number and k is the Boltzmann constant and alpha m is the constant for the given substance. It represents the diamagnetic molar susceptibility of the substance induced by the applied magnetic field. In equation 11, all quantities are constant except Xi m and T, thus determining Xi m for the given substance at different temperature T, and then plotting Xi m versus 1 by T. A straight line graph will be obtained, the slope of which will be equal to mu m square n upon 3k. Thus mu m can be calculated. The unit of mu m are erg per Gauss. However, it is usually expressed in terms of Bohr magneton Bm. 1 Bm is equal to 9.2732 into 10 raised to power minus 21 erg Gauss inverse. Relationship between magnetic moment and the number of unpaired electron. The total magnetic moment of an atom, ion or molecule is the sum of the following two values. One is the magnetic moment due to the orbital motion of the electron. It is equal to under the root L into L plus 1 Bohr magneton, where L is azimuthal or orbital quantum number for that electron. Second is magnetic moment due to the spin motion of the electron. It is equal to 2 under the root S into S plus 1 Bohr magneton, where S is the spin quantum number having value equal to half. If ions or molecule are considered instead of 3 atoms, it is expected that the orbital motion of the electron are tied into the nuclear configuration of the molecule or the ion so tightly that they are unable to line up with the applied magnetic field. Hence, the magnetic moment contribution to the orbital motion is negligible. Thus, the magnetic moment of the molecule or the ion is mainly due to the spin motion of the electron. Hence, it is called spin magnetic moment. Thus, we have mu m is equal to 2 into under the root S into S plus 1 Bohr magneton, that is equation 12. Hence, S represents the spin quantum number for one unpaired electron for a molecule or ion containing a number of unpaired electrons. The expression is usually written as mu m is equal to 2 into under the root S into S plus 1 Bohr magneton, equation 13, where S represents the total spin quantum number. Thus, for one unpaired electron, S is equal to 1 by 2. For 2 unpaired electron, S is equal to 2 by 2. For 3, S is equal to 3 by 2, and so on. In general, for n unpaired electron, S is equal to n by 2. Hence, equation 13 become mu m is equal to 2 into under the root n by 2 into n by 2 plus 1, and mu m is equal to under the root n into n plus 2 Bohr magneton, that is equation 14. Thus, knowing the number of unpaired electrons present, the magnetic moment mu m can be calculated, or vice versa. The expected value for the magnetic moment mu m for paramagnetic substances for different values of unpaired electron are given in table 5.4. Relationship between molar magnetic susceptibility and the number of unpaired electron. Taking alpha m to be negligible in equation 11, as it represents the diamagnetic molar susceptibility of the substance induced by the applied magnetic field. Equation 11 becomes Im is equal to mu m square into n upon 3 kt. that is equation 15. Substituting the value of m from equation 14 in equation 15, we get xi m is equal to n upon 3 kt into n plus 2, that is equation 16. The expected value of xi m for different value of n are listed in table 5.4. Application of magnetic susceptibility. First, in confirming the structure of a given molecule. The use of molar magnetic susceptibility in confirming the structure of a given molecule is based upon the fact that magnetic susceptibility is additive as well as constitutive property, as already discussed in session with example. In calculation of the number of unpaired electron in a molecule or ion. Knowing the molecular magnetic susceptibility xi m, which can be easily determined experimentally, the number of unpaired electrons present in a molecule or ion can be calculated using equation 16. This has help in understanding the electronic structure of a number of molecules. For example, the molar magnetic susceptibility of oxygen has been found to be 3400 into 10 raised to the power 6, which shows that it must contain 2 unpaired electrons. Thus, the structure of oxygen molecule should be represented as. Third, in the study of coordination compound. The main application of magnetic susceptibility in chemistry have been in the study of coordination compound of transition metal. Measurement of magnetic susceptibility help us to know the number of unpaired electrons present in the complex, which in turn helps to assign the correct structure to the complex ion in some cases. For example, the magnetic susceptibility value of the complex is FeCN63 negative and Fe(F63 negative through each, thus the same coordination number suggests that this is one unpaired electron present in the former, whereas there are 5 unpaired electrons present in the latter. These are explained by suggesting the following electronic configuration to this complexes. Iron atomic number 26, electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. And after losing 3 electron, Fe3 positive, electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Fourth is in establishing the formulas of certain compound. For example, it has been shown that the formula of hypophosphoric acid is H4P2O6 and not H2PO3. It is because if the latter formula were correct, sodium and silver salt NaHPO3 and Ag2PO3 would contain an odd electron and should be paramagnetic, while actually they are diamagnetic. As these salt must have the formulas Na2H2P2O6 and Ag4P2O6 respectively. Similarly, the formula of mercurous chloride is Hg2Cl2 and not HgCl. Fifth, in explaining the existence of odd electron molecule. The molecule containing odd electron are expected to be paramagnetic. It is actually found to be so far for a few gases compound, namely nitric oxide, nitrogen dioxide and chlorine dioxide. Moreover, their magnetic susceptibility shows that they contain one unpaired electron in each case. Sixth, in explaining the formation of free radical, some highly substituted aromatic compound have a tendency to dissociate for fragments called free radical. The existence of free radical is supported by the fact that such substances exhibit appreciable paramagnetism, which is explained on the basis that the free radical contain odd electrons. The measurement of magnetic susceptibility of substances even help in the calculation of percentage dissociation of the substance into free radical. For example, the paramagnetic susceptibility of alpha-naphthyl diphenyl methyl is found to be 140 into 10 raised to the power minus 6. The theoretical value for a single unpaired electron as shown in table 5.4 is 1260 into 10 raised to the power minus 6. Hence, percentage of compound dissociated into free radical is 140 upon 1260 into 100, that is equal to 11%. Our chapter is completed. Thank you.